This is lecture 3L for Calculus 1, and here I'll discuss some applications. One application of differential calculus is to compute the rates at which things are changing, the rate at which an object is falling, and then the second derivative would be the acceleration associated with that object. So I'm going to show an example here for just an object that's dropped or launched from the ground. Since we have single variable calculus, we can only have one independent variable. In this case, it's going to be time. So what this represents is an object either being shot straight in the air and then coming straight back down, or an object being dropped from some height and falling straight down. In this equation, y is the height of the object above the ground. Okay. y0 is the launch height, or the drop height. This is a v0, and that means the velocity that you initially impart to the object. If you shoot it out of a cannon, it's the velocity it has when it leaves the cannon. If you just open your hand and let the object go, assuming you're not moving either up or down, then this would be 0. And here's acceleration due to gravity. On Earth, it's 32 feet per second squared, or 9.8 meters per second squared. Make sure your units match up. If I take the first derivative, the derivative of y with respect to time, and y is the height above the Earth, that will give the velocity at which the object is moving. If I take the second derivative, I will get the acceleration that the object is undergoing, and if I take the third derivative, I will get what's called jerk, or lurch, or surge. So here I'm going to take the first derivative with respect to time, and that will give me the time-dependent velocity. So I have to apply the d by dt to each term in the equation. So d by dt times y0. y0 is just a constant, so that's 0. Then I take the derivative with respect to time of the term v0 of t. v0 is a constant, and if I'm taking d by dt of t, that's 1. So I just get v0 here, which is the initial velocity. Now I'm taking the derivative with respect to time of a constant a over 2 times t squared. The derivative of t squared is 2t. The 2's cancel, and I get minus at. So by taking the first derivative with respect to time of a displacement function, like y being the height of the object, then I get velocity, and the velocity will vary with time. When t is 0, when t is 0, this term is out of the picture, right? Okay. So all the velocity at time 0 is v0. That makes sense because that's how we set up the problem. Always check those little things like that, because if you don't, somebody else will, and it's very embarrassing. Okay. And if t is greater than 0, well then this last term is back in the picture. We have this whole expression here. If t is greater than 0, then the velocity of the object is influenced by gravity, a being the acceleration due to gravity. Now I'm going to take the derivative of velocity, which is the second derivative of the displacement. So I'm taking here the derivative of the velocity that we got on the other page. So the velocity was v0 minus at. I'll just put that right there. And I'm taking this derivative, but I want to point out that here's a d by dt, and what is the velocity? That is the derivative of y with respect to time. See the 2d's and the 2 dt's? Perhaps you watched the lecture on higher derivatives. Right, that is written d squared y dt squared. Nothing is squared here. It just means the second derivative. It means you took one derivative. When you're done with that, you took another derivative. So here, this was a result of the first derivative. I take a derivative of that. Derivative of v0. v0's a constant. That's 0. Derivative of minus a times t is just minus a. That is the acceleration of the object, and that makes sense. It's undergoing acceleration due to gravity. That is the acceleration due to gravity. It is negative because it's being pulled back down to the Earth. Now let's take one more derivative, and the derivative of acceleration is jerk. So I'm taking the derivative of the acceleration of the object. It's not minus a, it's just acceleration of the object. Sorry, that was bad terminology there. Okay, what is this? I want to point this out. You're taking the derivative of something that was the second derivative. Okay, because it was the second derivative up here. So if you're taking that second derivative, how many d's have you got? 3. So you write it like this, meaning you're taking the third derivative of the expression for the height of the object. Nothing's cubed here. It means you took the derivative 3 separate times. So right here was the result of taking the derivative twice. I take it once more, I get 0. There's no jerk. It's smooth, except there's no jerk. The acceleration is minus a, and that's it. It's a constant, so the next derivative is 0. Well, now instead of having an object that's dropped or launched straight up, let's just say we have an equation of motion for this particle. We can give the displacement or the position of the particle by this equation. Right now we don't see any terms due to gravity. Maybe you're in some kind of an accelerator. Who knows where this particle is. And let's say it's described by t cubed minus 6t squared plus 9t by this polynomial. The first derivative with respect to time gives the velocity of the particle. When I take the derivative of this, I get 3t squared minus 9t plus 9. When I take the second derivative, means I take the derivative of this. That's the result of the first derivative. I take another derivative, the 2 comes out, I get a 3t, and then I get a minus 12. In this case, I could take that third derivative, and the derivative is not minus 12, it is 6. I guess we've got to fix that up. So cancel that. The jerk is, when you're taking the derivative here, you would get a 6. Because the derivative of t is 1, but the derivative of the minus 12 is 0. Okay, that's okay. I'm going to leave it like that. So the point here is if you have an expression for the height of the object above the Earth or the position of the object, you have it with respect to time. Then if you take the first derivative, you get the velocity. If you take the second derivative, you get the acceleration. If you take the third derivative, you get the jerk. So all you have to do is continue to take these derivatives. Remember, to take the third one, you had to take the second, which means you had to take the first. So you take them in order. And you get velocity, acceleration, and jerk, starting with the position, an equation or an expression giving you the position as a function of time. Now I want to talk a little bit about applications in physics and chemistry. Often you have these very, very complicated laws, and you only want to look at 2 variables at a time. All those other little terms can get in your way and bother you. So what you can do is lump all of the things that are constants that you're not working with, lump them as a C. Okay? Or you can assign them some Greek letter like alpha. They do this in chemistry and physics all the time. And then they call it a new name, a new law, give it a new name. Here's an example. Here is the ideal gas law. Pressure times volume equals number of moles times the universal gas constant times temperature. You've probably seen that already. Okay. Now, if you want Boyle's law, all you care about is the pressure and the volume. So the nRT gets replaced by a C, okay, where C is equal to the nRT, and you say pressure times volume equals a constant. So you took all the things that were constant and lumped them as a C. How about Charles' law? All you care about is the number, you care about the temperature and the volume. So you take nR and P, which are held constant, and replace them with a C. This makes your life easier. Here's an example of doing that. Say you have the ideal gas law, PV equals nRT. Right. And you want to see how the volume changes with pressure. That's called taking the derivative of the volume with respect to pressure. Now everything we've done in calculus so far, we're just using. We don't have to derive anything. All we're doing is applying it. Okay? So you can take derivatives with respect to any variable you want. We're used to using x and t, but you could just as well use p. Okay? So I lumped everything I didn't need into this constant c. And here's my law, c over p. I take the derivative with respect to pressure. It means you go d by dp. Here's my operator right here, d by dp, and it's operating on the function c over p. Well, the c can come out in front, and I'm taking the derivative with respect to pressure of p to the minus 1. It's as though you had d by dx, and then what it was operating on was 1 over x. You know how to do that. So p is just a variable, and you can go ahead and do this calculation. Took the derivative of p to the minus 1, the minus 1 would come out in front, and the minus 1 would decrease by 1. So you would end up with minus 1 over p squared, right? And here's the constant. This place you can just, now you can just replace the constant with the values, minus n over rt divided by p squared. So the point is, take anything that's a constant, if there's a bunch of them, lump them in as a c, or as an alpha, something like that, and then you can get them out of your calculation. Second thing, you can take the derivative with respect to any variable. It doesn't have to just be x and t. Now I want to discuss another equation that you might see. They use this in medicine for blood flow, and it's not really a very good model. It's called Poiseuille flow. I didn't write it in there. Poiseuille, Poiseuille, or laminar flow. And what it is the flow in a circular pipe of radius r. You see why they want to apply it to a blood vessel. And the pipe has a length L, and it has a constant radius. Delta P is the pressure at either end of the pipe that's driving the fluid through it. It's got some fluid going through this pipe. You assume the fluid has some viscosity, which is eta, and it also assumes a uniform fluid, and assumes that the viscosity is constant, which may or may not apply, which does not apply to blood flow, but it's used. At any rate, it is used for laminar flow of fluid through pipes, so you'll see this quite a bit. So I'll just discuss this a little bit, so you'll have an introduction to it. V is not the velocity, this is the volume flow rate, but it's similar to velocity. It's how fast the volume's moving through this pipe. So here are my terms. Delta P just means the difference in P, and right now it's just a static number. If you had so many, so much pressure on one end of the pipe and a different pressure on the other, delta P is just the difference between those pressures. 4, okay, you need that scaling factor 4. Eta is the viscosity. You can look that up in a table if you need that. L is the length of the pipe. R is the radius, the outside radius of the pipe, and R is how far you are from the center to the edge. See, R is less than or equal to big R. Here are some pictures of the situation. So here's my pipe. Here's little r. R is 0 if you're right in the middle of the pipe. R is big R if you're out at the edge of the pipe. And the force F, which would be that difference in pressure, is pushing fluid through this pipe. Well, here you see that. No, that F is the flow. I'm sorry. Here's P1 and P2. So that gives you, the difference gives you the pressure drop across the pipe. And some fluid is going through there. What does the volume flow rate look like in laminar flow? It's very interesting because the fluid, actually you could approximate it by a bunch of concentric spheres, or cylinders. All right? And in each cylinder, like at a certain radius all the way around the center, the rate is constant. You move out to another radius, that rate is constant all around. So it's like a bunch of tubes all nested together, and that's what this is showing. See, R is the radius all the way to the edge of the pipe. Little r is how far you are off center. And this is right in the middle. And look where the flow rate is the maximum. It's maximum in the middle, and actually at the edges it is 0. Very interesting. Okay, let's say I want to take, well, here's my equation right here. I'll get the marker. Here's the equation right here. And I'm going to study this equation. I want to find out how the volume flow rate changes with respect to the distance from the center of the pipe. That would be little r. So all these terms here are constant, so I just give them c and I don't have to carry them around with me all the time. Okay. Now I have a simpler equation. I want to take the derivative with respect to little r. Here's the derivative with respect to little r. Here's the c. It's a constant multiplier, comes out in front. Then I can take the derivative of the first term and subtract the derivative of the second term. Okay, here's the c, no change there. Big R is the outside radius of the pipe. It's not changing with little r. So that derivative is 0. Okay, good. Now I take the derivative of r squared and I get 2r. There was a minus sign, so I have minus 2r. At this point, I've taken my derivative. I can reassemble things to get an answer. Derivative with respect to r of the volume flow rate equals, I'll restore my c's, so delta p over 4a to L multiplied by minus 2r, and I can combine this equation. Obviously, I have forgotten the negative sign, so I better write that in right now. There we go. Okay, sign error fixed. This tells me how the volume flow rate changes with respect to r, the rate at which it's changing with r. It varies directly, right, linearly with r. I can take the derivative with respect to big R to say, well, does it matter that flow? How does that flow matter change? That volume flow rate change if I have a big pipe versus a little tiny pipe? Okay, so I take the derivative with respect to big R. Again, I lump all those constants that were just out in front with one letter c. I'm taking the derivative with respect to big R, pull that derivative operator through, and the derivative with respect to r of big R squared is 2r. This isn't changing, we're just leaving that constant. We're not interested in that variation. So reassembling, this is what I get. Again, that varies linearly in a positive direction. Now we could say, what is the acceleration? If this is a volume flow rate, it's changing with time, I could take one more derivative and get the acceleration. Okay, let's try it. I take the derivative with respect to t. Does the pressure change? Say nothing's changing. Does p change with time? No. 4 doesn't. Eta doesn't. It's the same fluid. The length doesn't. These two numbers are constant. Well, in this case, the acceleration of this fluid, wow. I have nice length. Okay, it's 0. Right. The purpose here was to demonstrate taking complicated laws in physics or chemistry that have a bunch of variables in them. If that variable doesn't change with your problem, lump it all together as a constant. Then you can take the derivative with respect to any variable as long as it's not buried in the constant. After you get done with the calculation, then you reassemble.